and the Bernstein Center of the category of smooth WK-GLNF modules.
Well done. OK, so first of all, just as a disclaimer, this doesn't have anything at all to do with my talk, but I wanted to leave it up because someone clearly doesn't want it erased. So this way, if I get bored or you lose the thread or whatever, you can spend your time figuring out exactly what that's supposed to be. And I'd be interested if you do. OK, but anyway, as the title suggests, I'm going to be talking about the Bernstein center of the category, a certain category of representations of GLNF. And I want to begin by talking about some category theoretic preliminaries, just describing what this sort of Bernstein center is. So let me start by defining the center of an abelian category. So A here is an abelian category. And then the center, Z of A, is, well, in highfalutin terms, it's the ring of natural transformations from the identity functor of A to the identity functor of A. And as usual with category theoretic definitions, it requires a little unpacking to figure out exactly what this definition is. So equivalently, if you have an element x in Z of A, well, that's a natural transformation from the identity to the identity. And so it consists of a morphism inside A from every object of A to itself. So it's a collection xm for m an object of A, where xm is just an endomorphism from M to itself. But of course, you can't choose this collection arbitrarily. So in order for this to define a natural transformation, there's a diagram that has to commute. And what that diagram is anytime you have a morphism f from m to n, you can make a diagram like this, where this arrow is xn, this arrow is xm, and you want this to commute for all m and n objects of the category. So this is a ring because we can compose endomorphisms and we can add them to themselves. And moreover, it's a ring that acts naturally on every object of the category. It's also clearly commutative just because of these diagrams. You can make both of these, both the horizontal and vertical arrows, elements of the center, and then the commutativity of the diagram tells you that the center actually commutes with itself. And so the standard example, in fact, in a certain sense, the only real example, is that if R is some non-commutative ring, and A is the category of right R modules, then it's not so hard to see that the center of A is actually just the center of R. Certainly the center of R acts on every right R module in a way that's compatible with all morphisms of right R modules. And on the other hand, by considering the action of A on the free right R module of rank 1, you can see that there's really nothing else that can happen. Question?
You say it's a ring, but isn't there an issue of smallness?
Yes, you're right. I tend not to think about such issues, unfortunately, but yes. I'm certain that that comes into play. Okay. Okay, so the reason, So the reason this comes up in the context of representation theory is that if you're thinking about the representation theory of finite groups, of course, the center of the group ring plays a very big role in that theory. And so if you have some more complicated category of representations, say a category of smooth representations of some locally profinite group, you might want an analog of the center of the group ring. And this theory of the center of the categories, in the context of representation theory, it's called the Bernstein center, actually provides this analog for you. OK, so, before I leave the abstract setting and focus on representation theory, I should say one more thing, which is that if E is an idempotent, in this ring, then what that gives you, what it's equivalent to, in fact, is a canonical direct sum decomposition of every object in the category. Namely, that object breaks up as EM direct sum 1 minus EM. And this direct sum is canonical in the sense that it's compatible with every single morphism in the category. And so we actually obtain a decomposition of the category itself as a product of two categories, whereby EA here, I just mean the full subcategory of A consisting of things on which this idempotent acts via the identity, and 1 minus E is the full category where 1 minus E acts as the identity. And if E is a primitive idempotent, then EA is called a block of A. So this is going to be important for us in just a second, because what will turn out to happen is that when we look at a category of representations, very often, well, at least of a large enough group, very often there will be infinitely many blocks in the category. The center will be some huge infinite product that's very hard to get any sort of concrete handle on. But on the other hand, the centers of individual blocks will be nice. OK, so that concludes the abstract nonsense. Let me get more concrete. So let me let K bar be an algebraically closed field of characteristic L. I'm going to let L be the field of fractions of the Witt vectors over K bar, and L bar is just the algebraic closure of L. And for the most part, we'll either be working over K bar, the Witt vectors of K bar, or L bar, mainly because I don't want to discuss descent at all. And now I'm going to take some finite extension of QP with P not equal to L, and I'm going to let my group G be GLN of F, and I want L to be fairly large relative to N. In particular, I don't want L to divide the order of the Weil group here, so I'm going to assume that N is less than L. Okay, and this assumption will be enforced, well, this assumption will be irrelevant when I talk about past results of Bernstein and Deligne and Vigneris, but it will be very relevant as soon as I talk about anything I've done myself. OK. So now let me define the category I want to talk about. a smooth W of k bar adjoint G module. And you can fill in k bar or L bar here as you like. This is a W k bar adjoint G module V such that for all elements of V, there exists a U inside G open and compact that stabilizes V. So we're considering not arbitrary representations of G, but representations of G that satisfy this auxiliary topological condition. And because we're imposing this extra condition, that means that the center of this category is going to be different from the center of the group ring attached to G, which is good because the group ring attached to G is hideous. OK. So, there have been a lot of study of these things, of course, and in particular, there's been a lot of study of the center and block decompositions of categories related to this one. So let me drop a few names. Bernstein and Deline described rather than computed here, described the blocks of the category of, well, let me say it like this, of rep L bar adjoint G, smooth representations of G with coefficients in L bar, and the center of each block. They turn out to be nice reduced algebraic varieties. There are also results of Vigneris more recently. So Bernstein and Deline did a lot more than this. They did this for essentially an arbitrary algebraic group G over a p-adic field, but always working over an algebraically closed field of characteristic 0. Vigneris worked specifically with GLN, and he described the blocks of the category of smooth representations of G over a field of characteristic L. She did not, however, describe the center of the blocks, and that's something that instead, well, at least when L is greater than N, is going to fall out of some things I have to talk about today. Okay. I should also mention it's not directly related to things I'm going to discuss today because it deals with the L equals P case, but in the case where the group is GL2QP and you're working in residue characteristic P, Pascunas has some recent results describing a closely related version of this Bernstein center. It's actually a completed version of this Bernstein center, and that has turned out to have spectacular applications for a p-adic Langlands. So this has a similar flavor, but it's in the much more tractable case where L is not equal to P, and therefore one has things like Haar measures. Okay. So let me begin the detailed part of the talk by describing what happens in characteristic 0. So all of this is in the context of Bernstein and Deline. And in order to do that, I have to talk about parabolic induction and restriction. So for P equals mu, a parabolic subgroup of G. Here M is the Levy subgroup and U is the unipotent radical. We have two functors, which I'm going to denote by I from P to G, and restriction from G to P. So this goes from representations, coefficients in anything really, of the Levy subgroup to representations with coefficients in G And the parabolic restriction is an adjoint. It goes in the other direction from representations of G, well, smooth G modules. I'm calling the field K bar. Back. So there's an adjoint. So these are exact, first of all. I'm not going to explain too much how they're defined, except that they do involve induction and restriction. And if you don't know what they are, what's going to be important for us is that these form an adjoint pair. So Helm in the category of representations of G from A to the parabolic induction of B, that's equal to Helm in the category of representations of M of the parabolic restriction of A to B. So the point of these is essentially that they let you build interesting representations of GLN out of representations of smaller GLIs. Any Levy subgroup is conjugate to a block diagonal subgroup, and an irreducible representation of that Levy is then just a tensor product of irreducible representations of smaller GLNs. And so one can build a representation of the larger GLN out of a bunch of smaller ones. And then the parabolic restriction actually lets you detect when a representation does in fact, well, at least admit a map from something built out of smaller groups. Okay, so a natural question to ask, and this theory goes back to Bernstein and Zelevinsky, is essentially what representations of G arise from smaller groups? How can we detect that? And sort of in how many different, if we can build a representation of G out of a representation of these smaller GLNs, well, in how many different ways can we do it? And the answer to that question comes from the theory of cuspidal support. So let me make a few more definitions. So a smooth WK adjoint G module pi is cuspidal if it's killed by all of these parabolic restriction functors. So if our GP of pi is equal to 0 for all P subset of G proper and parabolic. So that's one. There's also a closely related notion that's actually the same in characteristic 0, but only applies to really to irreducible things. So I'm going to say an irreducible representation pi of G over a field, so over either K bar or L bar, depending on what characteristic we're in, is supercuspidal, not merely cuspidal, if pi is not isomorphic to a subquotient of any IPG pi prime with P subset of G proper and parabolic and pi prime a representation of M, the Levy subgroup. Okay, so let me make a few remarks about these definitions. Maybe I'll make them over here, actually. So first of all, because of the Frobenius reciprocity, the adjointness of parabolic induction and parabolic restriction, if pi is irreducible over little k bar or L bar, then pi is cuspidal if and only if pi is not isomorphic to a quotient of any IPG, of any parabolic induction. So the difference between cuspidal and supercuspidal is really the difference between the word quotient and subquotient appearing here. In particular, supercuspidal always implies cuspidal. In characteristic 0, in fact, the converse is also true. These are completely equivalent notions. So over L bar, cuspidal implies supercuspidal. And if that were the whole story, I'd have wasted a lot of time in defining the two notions separately. But it's not the whole story. Over K bar, supercuspidal is a strictly stronger condition than cuspidal. Question? Yes, I guess. In fact, one can do it either way. But you're right that submodule is the one that comes out of Frobenius reciprocity. So maybe that's the one. Ah, OK. Well, you know more about P equals L than I do. So fair enough. OK, submodule then. OK. So those notions themselves are important, but essentially, well, in characteristic 0, what turns out to be true is that the supercuspidal representations, or equivalently the cuspidal representations, are basically the atoms of the theory of the classification of irreducible representations of G. Every representation is built by parabolic induction in some sense, well, and taking subquotients from supercuspidal representations of some smaller group. And reflecting that fact, we have the notions of cuspidal and supercuspidal support. So let me take a representation pi that's irreducible over either k bar or L bar. And there's a theorem, then, that's due to Bernstein, Zelevinsky in characteristic 0, and due to Vigneres in characteristic P, that basically says, first of all, there exists a pair, M pi prime, with pi prime, well, maybe I should actually, let's leave it like this. With pi prime cuspidal and irreducible representation of M over either k bar or L bar, whichever one pi is defined over, such that pi is a quotient, or let me say submodule, just to parallel the definition up there, of IPG pi prime. So that's almost by definition. But the important part is that this pair M pi prime is unique up to G conjugacy. And it's called the cuspidal support. of pi. Okay, so that's part one of the theorem. And there's a similar statement with cuspidal support, with the word cuspidal replaced by supercuspidal, and the word submodule over there replaced by subquotient. So maybe I'll come back over here. So the second part, which only differs from the first part in characteristic L, and therefore should really be attributed entirely to Vigneris, is there also exists a pair, let's call it M prime pi double prime, with pi double prime supercuspidal, such that pi is a subquotient of IPG pi double prime, and M prime pi double prime is also unique up to G conjugacy, and it's called the supercuspidal support of pi. Okay, so because supercuspidal is a stronger condition than cuspidal, supercuspidal support is a coarser invariant than cuspidal support. In particular, there's also a notion of cuspidal support for Levy subgroups of M and supercuspidal support for those. And what you can do is you can say that the supercuspidal support of the cuspidal support of pi is just equal to the supercuspidal support of pi. So there's a certain transitivity that goes on. Okay. And now that I've built this theory up, I can actually describe the block decomposition of G over L bar. So these are the results of Bernstein and Deline on representations smooth representations of G over L bar. So, I do apologize. There's one more definition first. A pair M pi of a Levy subgroup and a representation is inertially equivalent to M prime pi prime if there exists some G in G such that G M G inverse is equal to M prime, and the representations pi conjugated by G and pi prime, pi and pi prime are inertially equivalent. It always helps when you're defining a term to write it down. If there exists a G in G, okay, better, such that the representations pi G and pi prime differ by a twist by an unramified character of M prime. So when I was talking about cuspidal support, I was interested in these pairs up to conjugacy. Here I'm interested in these pairs up to the combination of conjugacy and twisting by unramified characters. Okay. So now So now let's fix m pi with pi an irreducible supercuspidal, or cuspidal, it doesn't matter, representation of m over L bar. That's why it doesn't matter. And let's let rep L bar of G sub m pi be the full subcategory of rep L bar of G consisting of modules V such that every irreducible subquotient of V has supercuspidal support inertially equivalent to m pi. So I've defined this full subcategory, and there's no particular reason from what I've said so far to expect it to be anything nice. But in fact, the result of Bernstein and Deligne is that this is actually a block inside the category of representations. So rep L bar of G m pi is a block. So they've identified, by doing this, the primitive idempotence of this category, the center of this category. And moreover, they were able to give a very nice description of the center of each block. So theorem, again, Bernstein and Deligne, that the center L bar G m pi, this is a finitely generated reduced k-bar algebra, and well, let's call this thing Z sub m pi. And moreover, you can describe its L bar points very nicely. The L bar points of Z m pi are in bijection with the possible supercuspidal supports, or conjugacy classes of supercuspidal supports, in the inertial equivalence class of m pi. So in other words, with supercuspidal representations pi prime of m inertially equivalent to pi up to conjugacy. So to put that more succinctly, if you know what block an irreducible representation is in, you know its supercuspidal support up to inertial equivalence. And if in addition you know how the center of the category acts, then that pins down the supercuspidal support precisely, and that's all the information you get. The action of the Bernstein center recovers the supercuspidal support. Okay, so in fact, it's very easy to write this down explicitly. You can, once you know what its points are in the above sense, you can get a very concrete description of it. It's essentially so V sub m pi is, roughly speaking, isomorphic to a polynomial ring. Well, a Laurent polynomial ring, I should say. And then inside of that, you have the invariance of a certain Weyl group, well, a subgroup of the Weyl group associated to the levy. And And all this is saying is, well, if pi is a tensor product of some representations, well, it may happen that two of those representations are inertially equivalent to each other. And then you can twist the first one by one unramified character and twist the second by the other, or you can do it the opposite way around. And the action of this Weil group accounts for the fact that those two twists will be conjugate to each other. So this essentially gives you, each of these t's gives you a twist of one of the factors that make up the representation pi, and you might not care exactly about how those twists are ordered because the supracuspidal support is really something that only matters up to reordering. Okay. No, good point. Let me call this R instead. I don't want to make it precise. It's essentially the number of blocks of the levy. Okay. So that's Bernstein and Delian in characteristic 0. I said Vigneris had a block decomposition in characteristic L, and that just says that, and that exactly parallels the characteristic 0 theory. In other words, for m pi, with pi a supercuspidal, now it matters, irreducible representation of m over k bar, we can define a category, we can define a full subcategory rep k bar of g sub m pi. So again, any object in this category, for any object in this category, all of its irreducible subquotients have supracuspidal support in the inertial equivalence class determined by m pi. And that turns out to be a block of rep k bar of g. Okay. So that's the background. And I'm interested in doing a similar thing for the category of representations not over a field, but over the Witt vectors. So I want to find a block decomposition for the category of smooth WK bar adjoint G modules. And I would like some sort of description of the center of each block. So
even now there is no explicit description in the finite characteristic case.
Well, it will be the mod L reduction of the block of the center I'm describing, but
but it's not in Vigneris's theorem.
It's not in Vigneris's result. No. Okay. So again, when I describe these blocks, I want to describe them as full subcategories, such that every simple subquotient has a certain property. But now there's a new wrinkle, and that's that when you're looking at modules over the Witt vectors, you can have simple modules in characteristic L, and also simple modules in characteristic 0. So this is a pain, and it means that I have to make a somewhat awkward definition, which I apologize in advance for. But essentially what I'm going to do is define notions of mod L inertial supracuspidal support and mod L inertial cuspidal support for a simple W of k adjoint G module. So pi is now simple and smooth W of k adjoint G module. And so one possible W of k bar adjoint G module. One possibility is that L pi is 0. And in that case, the mod L inertial cuspidal or supracuspidal support of pi is what you think it is. This is just the inertial equivalence class of the supercuspidal or just cuspidal support of pi. So let's assume L pi is equal to pi. L is invertible on pi. So in that case, we have a representation over the field of fractions of the Witt vectors. And so we can base change it. Well, let pi tilde be an irreducible summand of the space change. Of pi tensor over L, L bar. There may be more than one, of course, because it's just something over L. Okay, so now we can let M pi tilde sub M be the cuspidal support of this new sum n pi tilde. So this is going to be a cuspidal representation of M over L bar. It's not going to be integral, because if it were integral, then pi tilde would be integral as well, and pi would be integral and it wouldn't be simple. So what do we have to do? Well, that's why I'm only defining this up to inertial equivalence. Whenever you have a cuspidal representation, you can twist it by an unramified character to make it integral.
Excuse me, I have a question about the second case.
Okay.
So here you have a W module, WG module,
Mm-hmm.
and you assume L is invertible.
Mm-hmm.
So you are telling us, let's forget the algebraic closure, maybe that is just an L module, an LG module.
That's correct.
How can this be simple? It is smooth, and how can it be simple under WG? Can you give an example?
So sure, let's take G equals GL1, and just take an unramified character on which Frobenius acts by multiplication by L. So then the inverse of Frobenius acts by 1 over L, and therefore it contains no G-stable lattice.
I see.
No, I say Frobenius, but of course I mean a uniformizer.
I see. And there are examples in higher rank which are not obvious reductions to these.
I mean, essentially the cuspidal support will fail to be integral in some way, exactly like the way I described. For a cuspidal representation, you're integral if and only if your central character is integral. And so it's not an issue.
So the Frobenius has to act in such a way as dilating any lattice.
Exactly.
Right, okay.
Exactly. Yeah. This is the same confusion as the fact that a variety over the Witt vectors can have some closed points in characteristic 0. It's the same issue exactly. And in fact, once we write down the Bernstein center, those will be the points that are non-integral on it. Okay. So this is the cuspidal support. We can twist pi m tilde by an unramified character to obtain an integral representation. And then we can let pi m bar be its reduction. Okay, so then m pi m bar is well defined, is now defined over k bar, and it turns out that this is well defined up to inertial equivalence. And this is the mod L. This is the mod L cuspidal, sorry, inertial. Inertial because it's only well defined up to inertial equivalence. Cuspidal support of the original representation pi. The mod L inertial supercuspidal support of pi is the supercuspidal support of M pi bar. So I'm implicitly using some facts that I haven't said out loud here. One fact that I'm using is that if you have an irreducible cuspidal representation, then its mod L reduction is also irreducible in cuspidal. That's very important because otherwise this would not be an irreducible cuspidal representation of M, and so you really can't call it the cuspidal support of anything. And one also, of course, has to check that this is independent of the summand you pick up here, basically because Galois permutes all the summands, and that up to inertial equivalence, it's also independent of the twist you chose. But that's
Actually, apparently the young people have seen this, but why is there an irreducible summand?
why is there an irreducible summand? So pi itself is irreducible and is therefore admissible. So its base change is also admissible, and therefore it has a socle. But I think it...
Oh, it's admissibility.
Yes. OK. OK. So right. So now that we have this notion, where do I want to go?
Theorem of Vigneras on the reduction of something irreducible.
Yes, irreducible and cuspidal. The reduction is irreducible. That's due to Vigneras as well. Practically the entire mod L theory is due to Vigneras in one form or another, or at least everything I'm going to use in this talk. All right. So now we fix an M pi bar irreducible and supercuspidal over K bar rather, and we set rep K bar, rep bit vectors over K bar of G sub M pi bar is the full subcategory of rep bit vectors of K bar G, such that every simple subquotient has mod L inertial supercuspidal support. Should really come up with an abbreviation for this, equal to, inertially equivalent to M pi bar. It's already an inertial equivalence class in its own right. So, so the first result, which is really already suggested to a large extent by the result of Vigneras, is that this is actually a block. Oh, yes. So I should say it hasn't mattered so far, but right here, now this assumption that n is less than L has to be in full force. I'm not making any claims at all when L divides the order of the Weil group. OK, so we have a block decomposition that in light of Vigneras' result is maybe not so surprising. Let's go on and see what can be said about the center. So unfortunately, I don't have as nice and canonical a description of the center in this particular setting as Bernstein and Deligne do in the characteristic zero theory. There are a lot of issues that intervene. At present, what I can do is come up with some explicit concrete description of these centers that depends on some choices, and that's a bit awkward to work with. And I'm working on trying to find more canonical descriptions. In particular, I have a conjecture that expresses the completions of these things in terms of Galois theory via the local Langlands correspondence. But for now, let me just state some of the fundamental facts. So the center Z sub m pi bar of this block pi bar is, first of all, finitely generated and reduced. Reduced is not so hard to see. L torsion free is also not so hard to see. Finitely generated really takes the explicit description. Should give a noun somewhere. Algebra over the Witt vectors. And its k points correspond to supercuspidal irreducible k-bar representations of M up to conjugacy. So the characteristic L points of the integral center look a lot like the closed points of the Bernstein center in characteristic zero. Moreover, this thing has some L-bar points. Its L-bar points correspond to conjugacy classes of pairs M prime pi prime with pi prime irreducible supercuspidal or cuspidal, doesn't matter. Well, let me say cuspidal to really highlight the difference here. Irreducible cuspidal over L bar up to conjugacy. Up to conjugacy that are inertially equivalent to pi. And over here, the equivalent condition is that the mod L is that this Levy subgroup need not be conjugate to M. In particular, this could be some representation of all of GLN even, whereas this could be something of a proper Levy. But the point is that what you require is that the mod L inertial supercuspidal support of this pair is conjugate to M bar pri bar. So whose mod L inertial supercuspidal support is equivalent to M pi. Yes?
K always is K bar, right?
K is always K bar, yes. It was K in my notes. Yeah. K is K bar here, here. Yes, everywhere. Okay. So as an example, there are certain situations when you have a cuspidal representation that's not supercuspidal, it will lift to supercuspidal representations in characteristic zero, and they'll be in the same block as the supercuspidal support in this. So this can glue together cuspidal blocks with principal series blocks in that particular way. And that corresponds to the fact that on the Galois side of the picture, you can have Galois representations that are irreducible but become reducible when you reduce modulo L. Okay, so I've got 5 minutes left, which is about enough time for an example and a conjecture. So I'll give one of each. So let me give an example where the description of the center of this block is fairly clean. So let's take pi bar, some supercuspidal representation, and tensor it with itself m times to get a representation. This is all over k bar of some standard Levy subgroup M. Okay, so now I can look for things with supercuspidal support just equal to this tensor product of m copies of pi bar up to inertia. So, and in general, that might be rather complicated, but let me make a key simplifying assumption. Let me assume that there does not exist a cuspidal pi prime over k bar with supercuspidal support inertially equivalent to any number of copies of pi bar. Oh, let's call this pi prime bar. So I don't want it to be isomorphic to any tensor power of pi bar for I between 2 and m. So unfortunately, if you tensor together enough copies of any supercuspidal representation, at least outside of banal characteristic, you'll eventually find some cuspidal thing with the same supercuspidal support. I'm going to avoid any case where that can happen by demanding this, by demanding essentially that n is small enough that this never happens up to the level m. Yes.
So pi bar is a supercuspidal of some GL? Or?
Yeah, it's some GL, let's say GL n over m of f. So that way, m, when I put together m blocks, I'll actually get a levy of GLN. Okay. And I don't want any intermediate things that are cuspidal but not supercuspidal and have supercuspidal support, some subset of this. This will essentially mean that the only cuspidal support with this supercuspidal support is the representation itself. Okay. So in that case, I can tell you exactly, well, almost exactly, what this pi tensor to the m is. It looks like W of k adjoins zeta, t inverse, modulo zeta to the L to the a minus 1, whole thing tensored with itself m times, and outside of that, you have once you tensor something with itself m times, you have an action of a permutation group on the tensor factors, and I take the invariance with respect to that. So what's going on here? Well, this one copy of this ring by itself essentially parameterizes lifts of pi bar. The T parameterizes the essentially the Frobenius twist, the twist by an unramified character, and the zeta tells you that there are also several different inertial equivalence classes that all reduce to pi bar, and the zeta tells you which inertial equivalence class you're in. This is the center, not the category. Z sub m pi tensor to the m. Thank you. Good. So essentially what you're doing here is you're taking all the possible ways of lifting pi bar tensored to the mth power in its mod L inertial equivalence class, and then you're modding out by the conjugacy action over here. And this is what you get. And that's fairly nice. Okay, that took longer than I thought. I have a conjecture relating the completion of the center at the point to the frame deformation ring of the corresponding Galois representation. Essentially, it should not be the frame deformation ring. Instead, it should be the basis invariant functions in the frame deformation ring. You'll see traces, but you won't be able to see things like the monodromy operator. And I guess I'll stop there.